Okay, so the annihilator for, we already agreed that the annihilator for e to the minus x, right? Because the derivative of e to the minus x is minus e to the minus x. So if I just add e to the x to the original, I would get 0. So that means the annihilator for e to the minus x is just the first derivative plus the original. Okay? And now for x squared, you always go one derivative past the degree. So I need a g cubed, because the first derivative of x squared is 2x. The second derivative is x, and the third derivative is 0. So you need 3 derivatives to annihilate it. Okay? So now our annihilator is g cubed times g plus 1. Okay? So now we're going to plug this into the differential equation. So here's the step I'm talking about. Look, substitute into differential equation, yeah? So we get, we apply the annihilator to this, so we get d cubed times g plus 1 times the derivatives of the differential equation, because I'm applying this on the left side. So this is d squared plus 1. And I'm applying this on y, right? And of course, I apply the same exact annihilator on the left, the one I found here. So this is g cubed times g plus 1, right, of e to the minus x plus x squared. Now, of course, choosing the right annihilator guarantees that this guy will go to 0. Now, that means, Ben, here, the characteristic equation, let's switch colors here, yeah? So the characteristic equation here is, so every d becomes an r. Yeah. Okay, but the trick, don't FOIL. Keep them factored, because that's when you can solve easily. So r cubed times r plus 1 times r squared plus 1 equals 0. And now you don't FOIL these. You keep them factored. And you set each one equals 0, right? Yeah. So r cubed equals 0, which gets you r equals 0, 0, 0. Or r plus 1 equals 0, which would get you r equal minus 1. Or r squared plus 1 equals 0, which would get you r squared equals minus 1, which would get you r equals plus or minus I. So you have this, and these two. Okay, so you have 6 roots altogether. So now you can write your y general. So y general will be, now the zeros will be the exponentials. So you get c1 e to the 0x plus c2 e to the 0x. But you remember, if this is repeating, you multiply it by x. Yeah. And then you also get c3 e to the 0x for the third root. And you also have, this is repeating, but you've already used the x, so you have to multiply by x squared. Okay, so that's the first set of roots, the 3 zeros. Plus, now, the minus 1. So this becomes e to the, so c4 e to the minus x, right? And then the last one gets you your sines and cosines. So we'll call this a cosine x plus b sine x. So these are all the roots. This is y general. Now, in order to get to my particular, I need to solve the original homogeneous. You follow? So, original homogeneous what's the original homogeneous? You set the right hand side equals 0. So now all we have is y double prime plus y equals 0. You write your characteristic equation and you get r squared plus 1 equals 0, which makes r squared equals minus 1, which makes r equals plus or minus I. These are your sines and cosines. No surprise here, because I know that my y complementary will be a piece. If anything, it will be a piece of my y general. Has to be, otherwise you've done something wrong, because this is getting you everything here. So then y complementary will be a cosine x plus b sine x, which is this part of your general. This is y complementary. So the rest, because technically your y general is equal to y complementary plus y particular. So if you take out your y complementary from this, the remaining terms, those are your y particular. So you just, when you solve the complementary, you take out the terms that you got for your complementary from general, and the remainings are y particular. So y, therefore, if I'm going to write my y particular, yeah, y particular will be C1. Oh, e to the 0, I forgot to knock these out. E to the 0 is 1, e to the 0 is 1, e to the 0 is 1. Okay? So my y particular is just C1 plus C2x, right? Plus, that's true, C3x squared plus C4 e to the minus x. So this is my y particular. This is the particular solution. No? This here in blue was the complementary. General minus complementary gets you particular. This one here was the general. Right. So the process is very simple. You find the annihilator of each of the non-homogeneous terms, whatever it takes to make them go away. You apply it to both sides of the differential equation, including the terms of the differential equation. You are guaranteed to transform it into a homogeneous differential equation, because the annihilator annihilates your non-homogeneous term, and you get 0. You find the characteristic equation of that new homogeneous equation. You don't foil. I think what the mistake you made here is you foiled this.
No, I didn't foil it.
You shouldn't foil it.
Yeah, that's what I did, I think.
You need to keep it factored so you can solve for the roots.
Right.
You get your roots, you write your y general corresponding to what these roots are. You go back to the original, you solve the homogeneous by setting the right hand side 0. You get the complementary characteristic equation, just like we were doing. You get the complementary. You take the complementary out of the general, you get your y particular. Y complementary has to be a piece of y general, otherwise you've done something wrong. So this summarizes the annihilator method used with the method of undetermined coefficients.